DatagenDV, Python Constraint Random Test Stimulus Framework. Abstract. This paper describes DatagenDV, a Python framework for generating C-compatible test stimulus using YAML and random constraint. The framework leverages multiple open source projects by typing them together into the base classes, which can then be extended by each user. This approach highlights Python's capability in creating custom verification framework with a simple user interfaces. Project timeline was significantly reduced by the DatagenDV's ability to leverage existing SystemVerilog constraints from block test benches. Introduction. Data generation is an essential part of design verification (DV). Without sufficient or valid data, verification projects are put at risk of not completely exercising the design under test duty. When tasked with creating a robust random stimulus testing for C firmware, we went looking for the best available tools. So Python's extensive source code libraries proved to be easy to learn and powerful. The PyVSC Python verification stimulus and coverage, which mimicked the SystemVerilog constraint randomization feature set, proved exceptionally useful. In the matter of a few days, a complex command structure with fully interconnected fields was correctly randomized by Python, and by converting existing SystemVerilog constraint from block test. The significant development time saved from this approach was, and then spent turning this access into a framework called DatagenDV, which could be used on future projects. The goal of this paper is to highlight the feature of the DatagenDV and how it leverages its imported libraries to create an easy-to-use framework. Although DatagenDV is written targeting a flow based on YAML and C, and each feature is largely independent, so it could be adapted to target other use cases. This paper should be useful to those interested in Python or those looking to generate stimulus outside SystemVerilog. We hope that DataGen will be an example to other DV engineers of Python's framework building capabilities and also give them inspiration in their own Python coding project. DatagenDV source code can be found at GitHub. Microsoft DatagenDV. Section 2 Related work. According to the IEEE, Python has consistently been the top programming language for multiple years. It's often used for verification infrastructure in place of older scripting languages. Python dominates the hardware adjacent industries such as machine learning, signal processing, and quantum computing, and has strong community and creating powerful open source libraries. One previous DVCON paper explored using Python's data science libraries to empower their scoreboard to perform a complex signal processing. So another submission shows interfacing with Python from SystemVerilog testbench through DVCON2023 to allow for complex data analysis as an alternative to MATLAB pre-generated the content. There are also several open source projects aimed at enabling Python as a viable option for verification. CocoaDB, coroutine-based code simulation testbench, aimed to fully replace SystemVerilog for simulator control. PyUVM is a Python implementation of a universal verification methodology, UVM, built on the top of CocoaDB. Although these prior works are related to the effort of this paper, the main difference is these efforts look to replace the SystemVerilog or tie Python into SystemVerilog test benches. DatagenDV instead brings the idea and the strengths of object-oriented seamless generation to an embedded C test environment using Python. The PyVSC is an open source effort to create a constraint randomization and coverage similar to a SystemVerilog. DatagenDV uses PyVSC as its randomization engine. The common alternative to the randomization piece is to leverage SystemVerilog randomization and dump the result to then be parsed and processed by another script before being passed onto the C environment. Although this method may be better for some situations, we found that keeping the entire pre-processing flow in Python was simpler to implement. Section 3. Approach. DatagenDV is an object-oriented data generation framework designed as a pre-processing steps for C routine using YAML specified test cases. As a Python-based framework, DatagenDV heavily leverages Python's robust and open-source libraries. The primary libraries it uses to accomplish its goals are the dataclasses to provide familiar SystemVerilog style class declaration with typing, ruamel.yaml, a PyYAML fork to provide a YAML in parsing which the loads and dumps the YAML the to and from Python classes. PyVSC, an open source library which enables test writers to write a SystemVerilog style constraint. ctypes, to provide C compatible types and generate binary data packed for C structure. The DatagenDV was originally designed as an augmentation and for existing flow where C firmware test had parameters specified in YAML. These C test cases were on-chip firmware and used for both simulation and emulation verification and post-simulation validation. When a test was run, YAML parameters were converted into C file with a struct created with values matching the YAML. This conversion was done by a script which existed prior to DatagenDV. The user had to provide a header file containing the structure definition. These files were then compiled with the rest of the C firmware. See Figure 1's dotted box outlined the flow prior to DatagenDV's introduction. DatagenDV streamlines this flow by creating a pre-processing step where test writers can generate more complex data for the C firmware to consume, for example, raw data, instructions, memory layout, and register values. When generating data for design verification in C firmware test, there are many drawbacks. Random constraint specification in C is not fully featured as SystemVerilog. Generation is performed using the DUT itself, which introduced ambiguity about the validity of the data, and it's difficult to validate the generated data matches the expectation of the test. In the case of pre-silicon verification, it's also beneficial to avoid extra cycles in the simulator to generate a stimulus. Moving this data generation step from C to Python eliminated these drawbacks entirely. Figure 1 is the DatagenDV data flow. The overarching goal of DatagenDV was to allow test writers to focus on the data they want to create and worry less about the underlying workflow. DatagenDV handles loading and dumping of the test configuration and support randomization and generate the supporting the test definition. Test writers specified their test configuration schema and the data they need to generate based on it, and the constraint for that data. They do this by creating classes extended the YAML primes-based class which DatagenDV provides. So A, building a Python framework. Part of the why the Python has become so popular is because of its ability to create complex frameworks with easy user interfaces. There are a few advanced Python concepts which are very helpful when creating a framework. The first is its reflection capabilities. This is important in a dynamically typed language since functions like type or callable help identify what the kind of data is passed into a function in order to appropriately process it. For even more dynamic and flexible functionality, a vars function allows code to access a dictionary of the variables in a class. The second advanced Python feature which is heavily used in framework building is decorators. Decorators tag a class or a function to modify or extend its behavior in some way. To those familiar with the there are many uses for decorators which give Python aspect-oriented functionality to modify and adjust classes after they have been declared. Similar to UVM macros in some aspects, decorators tend to be more elegant and powerful, so the data classes, the built-in library in Python, is one great example of how decorators extend the language in interesting ways. Listing 1. DataGen YAML primary-based implementation specifying YAML field. B. Familiar class structure and data classes. In most sub-object-oriented languages like SystemVerilog, class variables are declared up front and with a static typing. The transitioning to the Python dynamic typing to declares as you go style can be an abstract change of pace. This leads to engineers often avoiding the Python classes, overusing the Python dictionaries, instead leading to code that doesn't scale and is harder to maintain. Python's data classes live provides support for a more SystemVerilog style class definition. Data classes was added to Python's code libraries in version 3.7. Being a newer and optional feature, it's often overlooked by training and tutorials because data class is a very flexible, extendable library, and DatagenDV uses it as a foundation to connect all its other libraries is a straightforward interface. Verification engineers would be wise and consider data classes when starting their own Python project. Similar to UVM utils, macros in UVM, the @DataClass decorator processes the declared class and auto-generates a number of useful features. For each variable of a class, the user provides a name and a type, hint, and option or a default construct value. @DataClass generates the construct __init__ function and a method, and print, comparison, or sorting functions. It also keeps track of the declared typing of each variable. Although Python does not enforce type hints by default, DataGen's YAML primary-based checks loaded data against type hints during __post_init__ method. This type hints also provide essential information of the DatagenDV to convert the Python classes into C structs. Default values of class variables are specified using dataclasses.field. DatagenDV provides a wrapper for the field function, extending it to specify the additional attribute. For example, specify whether or not a field should be excluded when loading from or dumping back to YAML. These wrappers wrappers also safeguard users against the common gotcha of using a mutable default value, such as list seen in the listing 1. Data classes along with the DatagenDV wrappers provide a simple interfaces for YAML data. C is YAML class loading and dumping. YAML is commonly used in the markup language for verification tools. It has a strong focus on readability and pairs well with Python due to their shared syntax, scope based of the spacing, and list and dictionaries. This makes YAML a good choice for specifying the test cases at a higher level. One common issue seen when using YAML for many different scripts is that a schema often goes undocumented. So by encapsulating a script expected YAML inputs and outputs in a class, users of a script that have a clear location and lookup corrective usage. The DatagenDV also protects the user from typos in their YAML field names and ensures their typing matches. The DataGen-based class abstracts the detail of loading and dumping of the YAML away from the test writer. To parse YAML, and DatagenDV uses a fork for PyYAML library called ruamel.yaml, which is ruamel.yaml over PyYAML due to its filter of preserving the YAML commands and formatting, which is useful for easy diffing between originally modified YAML. Datagen YAML primary space class provides generic implementation of both to YAML and from YAML. These functions are specified by YAML ruamel.yaml and are called as needed to load and dump the class to the YAML. From the YAML relies on a field metadata set by the DataGen field function to avoid the dumping field, which were only meant for use by the Python framework. This is done by using the field function with the dir in. DataGen implements this by leveraging the metadata dictionary parameters of the data class field function. So by specifying the exclamation mark class tag and registering the class with the YAML parser. From YAML, ensure that both init and post-init are called. If a field should be concluded from the construct, and the field should specify dir out, the default value from this parameter dir in out can be used for values which may be specified as input but are also passed through the test. Note that the YAML.yaml does not call construct by default. Calling the construct ensures the default value from the data classes field defined are applied. D. Constraint randomization with the PyVSC. Now for the executive part, constraint randomization in Python. PyVSC is the open source Python. PyVSC is an open source Python library which mimics the feature of the SystemVerilog constraint randomization. Powered by the Bull-Lecter SMT solver, PyVSC can solve complex multi-variable constraints with randomization. For a full account of PyVSC features, we recommend reading an its-only documentation. This paper instead focuses on how DataGen integrated PyVSC into a framework. PyVSC relies on a Python introspection to find variables using special types, random int and random enum and etc. These must be declared in a class init function. Since the data classes live generate init, we must declare these as an additional field in the same manner as a non-random field. DataGen provides another data class field, wrapper function called random field to declare this properly. See listing the random field usage. PyVSC special types are not very easy to work outside of the constraint, so the DatagenDV flow recommends using the separated dedicated field for randomization and casting the data back to the standard types. DataGen provides a class decorator, the rand data class at rand_data class, to modify the user class to do this automatically. This decorator also applies a data class and a PyVSC rand object decorator. In order to use the same stimulus script for a variety of the tests without changing the Python code, DatagenDV provides a way to overwrite the randomizer field to fix values from the YAML by using a prefix of rand to denote the PyVSC constraint field. At rand_data class matches to each constraint field with a non-rand standard Python type field. At rand_data class extends the class post randomize function to copy the value back into a non-constant field. If a non-rand field value is not known when randomization is called, the at rand_data class will create an override in a constraint typing the field to the provided value. This allows the user to override the values from the YAML and control the randomization of the generated YAML. List 4 listing YAML. So the listing 4 shows at the start the framework class. In this example, we are using the construct directly to simplify it, as we discussed previously in section 3-C. DatagenDV calls the construct when loading a YAML into specified classes. List C is the PyVSC constraint applied to a DatagenPrem class. List 4 is overriding constraint, though the construct using the DataGen's rand_YAML_ override decorator. The E, PyVSC constraint analysis. Although the PyVSC is very impressive, there are caveats which are worth mentioning. Neither the time is taken nor randomized nor the evenness of the random distribution are optimized as most relevant simulator implementation. We found that the use of the PyVSC was more than sufficient, but recommended that any looking at a PyVSC should investigate and vet it against the scale and needs of their project. Luckily, Python makes it easy to test both performance and random distribution. Listing 5 shows how we can take the frame data class, randomize it many times, and then graph the result. The built-in various function return a dictionary copy of the object variables, allowing us to handle Python VS class implementation. MATLAB can be used to create a clear picture of what kind of distribution of randomization is providing. This would be more difficult to do in SystemVerilog, requiring an engineer to either use coverage tools to export result to be processed by another language, Python in many cases. The results from the straightforward example show the Python VSC's concurrent implementation doesn't provide a perfect distribution. However, it does not seem to neglect any values and judge the performance will enough on our work that it was better than alternatives. The time to randomize this option 10,000 took roughly 5 minutes. This is longer than a simulator randomization, but shorter than the equivalent randomization on embedded C code. This paper's primary goal is to deep dive into PyVSC's performance, but give a quick glance into current state and how users of DatagenDV can analyze their implementation. It shouldn't be expected. PyVSC has stayed the same since the paper was written either. Since starting the investigation, PyVSC it's received multiple updates and improvements in response to our bug report and feature request. The listing 5 is creating histograms to visualize random distribution. The bridging the language barrier to C. Once data is presented inside the DatagenDV, it needs to be saved out in a compatible format. YAML is often useful since it is human-readable and can be passed to the further infrastructure script. Data stored in a binary format has the benefit of being far more compressed than human-readable format. It can load it directly into a C struct without a complicated parsing if bit hacking matched. DatagenDV can both generate binary and header leveraging the Python's ctypes library. Ctypes has two main features which are useful to Datagen. C-compatible types in the C memory formatted by generation. These features seamlessly move data into a C environment from the DatagenDV classes. For more precise typing, DatagenDV users can replace standard Python type hints with the types like a C underscore into 32. DatagenDV can generate the struct definition of classes implemented in Python listing 6 and 7. To limit defining the common definition, DatagenDV also supports converting the Python constraint and enums into C defines and enum definites. These features help test writers greatly reduce their maintenance cost and may eliminate the opportunity for mismatches between Python and C data structures. The ctypes library also facilitates the creation of the binary files from the Python structures using types mentioned above. These binary files are useful when there are external constraints the size of the test compiled binaries. An example of generating binary output is shown in listing 8. These binary files can be loaded into C test by using fopen. Listing 9. Using the C header generated by the DatagenDV, a pointer to binary data can be created and used inside a C test. It is important to note that memory packing defaults of your compiler and ensure the ctypes library matches over, otherwise data will not be properly loaded. This listing 6 is the defining of a class of ctypes and generating a structure definition header file. Listing 7 is generated C structure is definition based on listing 6. Listing 8 is Python programming generating a binary file. Listing 9 is C programming loading a binary file. Chapter 4 Project Result. Multiple test benches and Microsoft have leveraged DatagenDV to create a more complex test stimulus for their C test. The test writers have reported that it took them a relatively short ramp-up period, and they were much more productive and using the Python to generate the test stimulus. Prior to generation DatagenDV being formalized in a generic framework, portion of each solution were used in the previous project for C chip level stimulus generation. In one project, a C structure with interdependent fields had randomized control parameters described in YAML, was randomized in the Python, and was written out of the binary object. Leveraging Python's random library allowed for significantly more randomization in shorter work clock time than if using embedded C in a simulation. In this project case, selecting between 10 possible values for a single enum was 6 orders of magnitude faster in Python than if randomized in C running a simulated processor. While it was easier to write a simple constraint to Python's random library than a C, describe the complex constraint with multiple interdependent values was a consistency issue. which limited the scope of testing. The process of implementing and turning these constraints using the Python's random library took multiple weeks of effort. If this project had leveraged DatagenDV, reusing block level constraint would have allowed for more complete stimulus generation at the chip level while reducing the amount of the effort from the weeks to days. Using the Python-based flow and recognizing the lab advantages it brought to silicon chip level verification informed the creation of the DatagenDV, recognizing the area of improvement. PyVSC was added to allow its more powerful constraint creation and its similarity with the SystemVerilog syntax. The common tasks of parsing the YAML and creating C headers and binary files were consolidated into common code for easily use. Additionally, switching from the dictionaries from classes using data classes provide a better abstraction and code reuse. Taking these lessons learned from the next project, more time was spent upfront designing how Python stimulus generation would be implemented. DatagenDV helped to bridge the gap between the UVM-based block level testing and the C firmware chip level testing. The DUT stimulus consists of complex instructions operating on the data into DUT's memory. The DatagenDV was set up to generate both these instructions and the data to be operated on. The creating a valid instruction and the data to go with them was very complex. Each instruction consists of 50 more interconnected fields. Instruction could also be co-independent through shared memory addresses to create sequences of instructions operating on the same data. Because PyVSC's syntax mimics SystemVerilog constraint syntax, UVM block constraint could be directly ported to the top chip level. An instruction with the contained 60 fields and 300 lines of SystemVerilog constraint was rewritten using PyVSC in a daytime. Replacing directed test case values, arbitrary chip-level constraints were then layered on top of the block constraint, allowing for a more complex interconnected randomization. Without leveraging logic constraint, it would have taken significant effort and ramp up for chip verification engineers to create a similar level of test stimulus. This same DatagenDV implementation also supported workflow from software architecture models. These instructions were simplified and only constrained a subset of a full instruction field. This test could be through the DatagenDV by specifying these incomplete instructions YAML, and the DatagenDV could fill in the blank and using the constraint solving. This showed that the DataDV-Gen's approach was flexible and adapting whatever the test parameters were available. Figure 3, the multiple test generation could be supported through the bidirectional constraints. So the one challenging initially when the DatagenDV, a large chip team was Python familiarities. Engineers who were already familiar with Python were productive almost immediately. However, those who had only used SystemVerilog were able to use this DataGen in a reasonable amount of time. They reported DatagenDV's familiar field of the type declared field and PyVSC's constraint solving helped them be productive even they didn't fully understand Python as a language yet. For those without C experience, using Python instead of C was a gentler learning curve due to its modern syntax and easier debug. On this project, we were able to delegate stimulus generation work in Python to those with less C experience and C-test firmware work to those with C experience. This mitigated the impact of working in so many different languages. Overall, the DatagenDV has shown to be a great benefit for our app project. We had seen a boost to productivity and increased coverage capabilities. As we continue to use it, we expected that it will be extended to support more libraries and use cases. The future work. DatagenDV is currently still in its infancy, and there are many areas which could be improved on. We are already looking at providing more direct support between C and Python. This would involve supporting for the dumping more complex nested data structure with the Python 2 binary. Currently, binary generation is mostly limited to the flat structures with the basic data types, and the ctypes doesn't support all packaging styles. For example, non-byte aligned DataGen could be enhanced to handle these cases. This would include support and testing of various operating systems and compiler. In the opposite direction, leveraging the system agency structure had to look to at with some success at generating C types, so the Python classes through the processing abstract syntax tree generated by Python-based C parsing libraries. DataGen could also be enhanced to support more direct support between the SystemVerilog constraint and PyVSC. The adapters of the DataGen will likely not have an identical test flow to Microsoft. To support other build flow, DatagenDV will be needed support to the additional configuration languages than YAML. Supporting languages such as XML or JSON would involve developing base classes to handle seamless parsing and dumping, leveraging the DatagenDV's other features. Since Python already has well-vetted libraries for most configured languages, this mainly would involve incorporating in with the DataGen's framework. This would enable compatible with other build flows across the verification industry. The open source verification tools like PyVSC are still new and need additional vetting. We encourage leaders to contribute to open source design verification libraries. By creating and improving these tools in industry can become more productive and reduce the in-house reinvention of verification framework. Chapter 6 is conclusion. DatagenDV has successfully saved hundreds of hours over several projects. DatagenDV integrates the open source Python libraries to enhance C-based data cases, enabling easy object-oriented data generation for more levels of verification. Using the YAML as an input to DatagenDV with the ruamel, the .yaml parser allows you for easier readable and modifiable test controls. By leveraging the PyVSC framework, DatagenDV enables the constraint random methodology verification. Engineers are familiar with and bringing them to the C test benching environment. Python's ctypes libraries DatagenDV the ability to easily generate highly compressed data which can be loaded into the C test. So the data class library acts as a foundation by providing a clear interface and extendable metadata. The strength of the DatagenDV is combining each of these tools together in an easy to implement framework. Python, the greatest strength is active open source culture, which enables innovation to build upon each other. We hope to share the DatagenDV. Other engineers will bring these ideas back into their own project. As more verification tools and frameworks are open sourced, verification will see more community innovation and higher quality testing options. Okay, thank you. Today, I read this paper, DatagenDV Python Constraint Random Test Stimulus Framework, was presented in a DVCON2023. Thank you for your time. See you next time.